All right. Okay. And you should be also able to switch on your videos now, those that have video. I've enabled it. Then I see a few people as well. Hi. Thanks. Okay. So how are the tutorials going, by the way? I've asked the tutors a bit, but maybe some of you can just unmute yourself and let me know if everything's going well with the online tutorials. Obviously, it's all a little bit less personal with this system. Is it working okay? Yeah. Okay, good. So like I said in my email to you all earlier, I saw that people are still watching the videos. A little bit less so in the last 2 weeks, I saw. So I'm hoping people are sort of with me. And I also said in the email that or the Moodle message I sent you, that I will have, I would try to finish with the material for the lectures by the Tuesday, hopefully, maybe a little bit run into the Thursday video of the penultimate week. So the week of the 12th, is it 12th of July? Yeah. So I hope that with the video on the 13th or on the 15th of July at the latest, we'll have all the examinable material done. And that will basically be, maybe I can show you already here briefly. So I have, let's go to the contents, table of content. Okay, so we've done chapters 1, 2, 3, of course, including the symplectic chapter that I've added. We've done the Newton chapter, and we are essentially gonna finish with the linear multi-step methods chapter by the video on Thursday. And then I'm going to focus for the rest of this lecture on boundary value problems and the section 6.1. So I will probably, this is part of finite difference, so I'll probably rename this 6.3.1, and I will add, as I said, I will add two chapters to section 6.4 will be on finite elements. So finite elements, of course, is a whole unit next semester in the autumn, if you're interested. But we're gonna do finite elements for 1D, finite elements for ODEs, which can be done in 2 lectures, basically. And then I will do one or 2 lectures on gradient and conjugate gradient method. So a few of you have been to the seminars that I have been offering this semester as well, where we did Krylov methods. I will pick out specifically the analysis of the conjugate gradient methods, because that is one of the most important methods to solve boundary value problems. So that's basically gonna be what's gonna keep us busy for the next 1, 2, 3 weeks. Yeah. So we'll have 3 more weeks on boundary value problems, and then the outlook to PDEs will be not examinable. But I will record 2 lectures, or 1.5. I think it'll fit in 1.5 lectures videos for that as well, to give you an outlook, which is then basically a kind of an appetizer for going to further numerics courses in the next semesters. Okay, and the other thing I did mention, and I still have no confirmation, let me just check my email if I got something. I did send an email earlier to check. Nope. So I was told that we would be getting the essentially the seminar rooms downstairs and in Mathematicon and the Hörsaal to do our exams on Friday, the 23rd of July in the afternoon. So I hope that that will be the case. If I'm just looking on the faculty page because they were usually advertising that on the faculty page. Does it say anything? Anybody have a look there already? Let's see. Klausurplan. Oh, that's Wintersemester. Yeah, that's from last semester. Okay, so I hope to be able to tell you soon that it's confirmed that we can do the exam on the Friday the 23rd. Okay. Is there any other questions regarding the sort of where we are at the moment and what we're still doing? I've just lost my Moodle page. Any more questions on that? Nope. Okay. So any questions to the course then? So like I said, the videos we are looking at the moment, I guess 17 and 18. So in 17 we were looking at the second part of the Newton chapter, and then the beginning of linear multistep methods. And in the lectures 18 we were looking at the consistency of linear multistep methods, and then we were in lecture 19, which I only published today, so I don't expect you to have watched that yet. We're looking at convergence, stability and convergence properties. So any questions? Yeah, sorry. Let me get the chat up. Yes. So in example, I'm gonna go to the notes, that's always the easiest. In example 3.5.2, okay, so this should be in the symplectic part. Okay, so in example 3.5.2, I don't understand how you get the square at L and the minus before M. Okay, let's see. So another simple and common example is the mathematical pendulum of a mass m swinging frictionless on a weightless string of length L subject only to gravitational acceleration g. Here the coordinate is the angle alpha, and the position of the mass at time t is uniquely determined by the initial release position at t equals 0. The kinetic and potential energies are given by, so t of alpha primed is a half mx primed squared and so I get the square at the L and the minus before ml squared alpha double prime. Okay, so we've got a half ml alpha primed squared, so we get the when we take the derivative of that, so let's see first of all what the Lagrangian is defined as. So the Lagrangian is t minus u. So we need to take these two equations here. So the Lagrangian is t minus u. Let me try to squeeze it in here. So Lagrangian is t minus u, and the Lagrange equations are total derivative d by dt of the Lagrangian with respect to the q prime variable is equal to partial derivative of Lagrangian with respect to the position variable. Okay, so the position variable in our case is alpha, and the velocity variable is alpha primed. And t is, so L in our case, I'm going to write it in red. L in our case is a half ml alpha primed squared minus, so there's a minus and a minus that cancel, so that's a plus mgl cos alpha. So now we need to take, on the left hand side, we need to take the derivative with respect to alpha primed of the Lagrangian, and of that the time derivative. So dl by dq primed in this case is, or dl by d alpha primed, let's write it in the correct variables already. dl by d alpha primed is essentially ml alpha primed times, exactly, ml alpha primed, and then dl by d alpha is minus mgl sine alpha. And then I need to take, for the first one, I need to actually take the time derivative, so d by dt of dl by d alpha primed, and that would be ml alpha double primed. So am I getting it right, or is the square still a problem? Yes, the square is still a problem. I think the square is a problem. I think the square is a mistake. Let's see. So now let's try and put them on the same side. So that would be ml alpha double primed is equal to minus mgl sine alpha. I think I missed the L. I think this should be already L squared. So I think the mistake is actually earlier. I think this is L squared because we definitely did an L there. Because you can sort of see it from the formula, because you have an x prime squared, and so the x prime needs to scale with length, and length L is sort of the length variable. So this, to get the same units, you need to have the x prime scale with L squared. But so there is a mistake in the original potential kinetic energy. Let me just see. I took it from these notes here. Let's see if I copied it wrong or if he has a typo. I copied it wrong. Okay, so there should be a squared there. So this is the change for the first question. And now let's look at the sign. The next one was a sign question. So let's see if I got the sign right or wrong. So if I bring this both on, no, the sign is correct, I think, because I think maybe you missed the minus from the derivative here. I don't know. Is that answering the first part of your question? Yeah. Okay. So there's a typo. It should be squared here for the L. Thanks for spotting that. Now the second question, I don't understand the first equality in the proof of 3.54. Okay. I get the delta P delta T times delta H. Well, this is a bit complicated. Delta P delta T. Oh, you mean D. The delta is the D. Okay. dP by dt times dH by dP. It's not times, but anyway, yeah. dQ by dt. Ah, okay. Okay, let's see what I get. So you need to think of this as being chain rule using 349. So we know that P primed, okay, let's again write everything down that we need. So P prime is minus dH by dQ. P prime is minus dH by dQ, each component. And Q primed, kth component, is plus dH by dpk. Okay, and then if I do time derivative of the Hamiltonian, which is a function of pt qt, then I need to do chain rule, and this is a vector value, so this is a vector, these p's and q's are vectors, and so we get essentially a sum over all these components, k equals 1 to d in this vector, and then we do derivative with respect to the kth component of p. That would be dH by dpk times inner derivative, which is dpk by dt, or pk dash. Let's just write pk dash. pk dash. And then for the second one, I get plus dH dqk qk dash. And now I'm substituting. So now I'm substituting here this one, and I'm substituting this one here, and then I get a minus from the first one, a plus from the other one, and so each of the terms cancels. So this is equal to sum k equals 1 to d, or let's substitute the other way around, then it's easier. Then we get a minus p, oh no, minus pk plus, sorry. If I'm substituting the other way around, it's a plus for the first one. So we get a qk dashed pk dashed minus pk dashed qk dashed. And so they all cancel, and this is 0. Does that answer it? But how do we get the pk and qk when we take the derivative regarding t from p and q? How do we get the... are you not able to unmute yourself? Then it's a bit easier to communicate maybe. How do we get the pk and qk when we take the derivative regarding t from p and q? So p is a function of t. So p is p of t, the vector p of t is p1 of t, p2 of t, all the way to pd of t. It's a vector valued function. And if you do the chain rule with respect to of the Hamiltonian with respect to t, because the Hamiltonian doesn't directly depend on t, it depends on t only through the function p of t, or p1 of t, p2 of t, pd of t. So it's, if you think about it this way, d by dt of f of g of t for scalar valued, scalar case, the chain rule just says this is df by dg evaluated at g of t times dg by dt of t. That's just the chain rule. And for vector valued, it's what I've written here. So it's dh pk evaluated at p of t q of t times dp k by dt at t. And that you have to do for every k, and then you have to sum up. That's the chain rule. Does that answer it? Mm-hmm. Mm-hmm. Oh yes, you're right. Thanks. I didn't even spot that, even though I was reading it 3 times now. Here, yeah? Yeah. Yep. So there's another typo here. Mm-hmm. Yeah, that might have been confusing you, Max, but I hope it's clearer now. More questions? Yeah. Yeah, I understand exactly what you're saying. Okay, let's go there. I think it's basically because we can define it as we want and then do the analysis. So you want to do a stability analysis plus a consistency analysis. As usual, you want to combine consistency with stability. And the way truncation error is kind of the notion. Maybe we should go first to the. Maybe I glanced over that by immediately jumping to the conclusions in the one-step method. Okay, so I'm gonna first of all look at the comparison between what we defined as the local error and the truncation error for the one-step method with what we defined for the multi-step method, which I guess is the question. So for the one-step method, we first of all defined a notion of global error. And global error is simply saying, okay, I want to solve the ODE up to a certain point Tn or capital T, and I simply define the global error to be the difference between the true solution at T, capital T, and the approximate solution at capital T. So that's kind of clearly the notion of globally over a window of time. That's the error I'm committing. Okay. So then we came to the local error. Now the local error is essentially saying I want to know what the so this is yk here. I basically define the local error to be the error you make in one time step. If I start with the correct, so the important bit being here that uk minus 1 or yk minus 1 is u at tk minus 1. We're really starting at the correct solution of the ODE at the time step tk minus 1, and we want to know how much error do we commit by simply one step if everything else was correct. Okay, so that's why we call it the local error, because it's essentially I start somewhere on the trajectory of the true solution, and I just see what in one step what error I make. Now I immediately defined the truncation error to be eta k over hk, but that's not. I mean, that's just a consequence of the definition of the local error, of the truncation error. What the truncation error really is defined to be is how much does the true solution not satisfy the scheme. So the scheme is this, yeah. So this is yk yk is equal to yk minus 1 plus hk f hk of tk minus 1 uk minus 1. And so what I define to be the truncation error is essentially if I think of this as a finite difference quotient, so you've got yk minus 1 divided by hk, and here you've got f of hk, tk minus 1, uk minus 1. How much does the true solution, if I do here uk, if I put here uk minus 1 divided by hk, then this is not exact anymore. So how much does the true solution not satisfy the approximation of our equation? That's what the truncation error is defined as. And then it happens to be that in this case, this actually reduces to simply eta k, the local error divided by hk. So bear that in mind. So the definition we really say for, and that's why it's called truncation error. It's the error about how much I truncate a Taylor expansion of my equation after, I don't know why people call it truncation error, but I guess that's how you can think of it. You could also call it a consistency error, or how much does the true solution not satisfy the scheme in some sense. Now let's go to the multi-step method, and if I haven't made any thought mistake, then with that definition in mind, then the definition we made makes sense. Hopefully, if I didn't make a mistake. Okay, so this is now the question. Here is the general definition of a multi-step method. So now the method is defined like this. So this is the scheme. That's the formula that the yk satisfied given all the yk minus the previous yks. And the local error is again saying, okay, if I assume that all the previous values are exact, so yk minus r is equal to uk minus r, then I define the local error to be the difference between uk and yk. Yeah, so that's the same notion as before. And for the truncation error, if you look at this formula in 5.6 here, then dividing this thing here by h, where's the equation here? Dividing this thing here by h, so I put 1 over h here and cancel it on this side. This, in some sense, is a linear combination of right-hand side, so that's like an approximation of the right-hand side. So we could, for example, do a polynomial approximation of the right-hand side on the at kth value given the previous values. That would be one way of approximating the right-hand side of my ODE. And the left-hand side is a finite difference quotient. It's just taking some linear combination of yk minus r's, dividing by h, and that's some finite difference quotient. So this is supposed to approximate y primed at tk. And this is sort of approximating f of tk yk. Yeah. So that's another way of seeing how a linear multi-step method, why a linear multi-step method is defined like it is defined. If you look back at the three examples we did, for the first one we essentially have used, here we have the formulae down here, down here. So again you have yk minus 1 divided by h is equal to fk, is the implicit Euler. Here we, in all of them for the Adams ones, we have always on the left-hand side simply yk minus 1 divided by h. But on the right-hand side, in this case, we have a half fk plus fk minus 1. That's another approximation of the right-hand side. So this would be the kind of the approximation of the ODE. And again, if you now ask yourself the question, if I stick the true solution into this u, how much does it not satisfy this? And that's again what the definition of the truncation error is. So the truncation error is again saying if I actually stick the true values in, so uk minus r, and I divide it by h, the whole thing here, then that's essentially how much the ODE or the approximation of the ODE is not satisfied by the true solution. And then we observe that the link between the two is this one. And okay, there's another reason why it looks so complicated, because I did only really define the truncation and local error in the explicit setting for a one-step method. Look here, I did it for the explicit setting. So this is done for explicit functions. So here it's explicit. Yeah. If for the other one, I also did it just for the explicit case. I hope you realize that. If you just look at the explicit case in this formula, in the explicit case, for the explicit case, beta s is actually 0. And so this is nothing else than uk minus sorry, I'm a bit confused. Okay, sorry. It took me a while. Okay, so here is the h introduced. Yeah, no, it's okay, it's correct. The h is here. I was just missing the 1 over h somehow. Okay, so if we look at the explicit case, then uk minus yk is LHU of tk. So it is the simple formula. For the explicit case, it does reduce to the simple formula. Now, if you now replace this by h times tau k u, then we have exactly the same formula as for the one-step method. So for the explicit methods, it is the same formula as for one-step methods. Do you see it? Yeah, because the defining property of the higher order linear multi-step methods is that we're taking different finite difference quotients here. So they have some coefficients. There are some pluses and minuses, like yk minus what the examples we had here, for example, that you see here. So you have these complicated formulae here, for example. So that's for example one example of an approximation of a finite difference quotient. Do you see here on this one? This is if I look at this formula here, then in the divide by h, then maybe let's not take the most complicated one. That's too long to write out. Let's take a less complicated one. Let's take this one, yeah. Then this one is nothing else than yk minus 4/3 yk minus 1 plus 1/3 yk minus 2 divided by h. That is an approximation times 3/2, I guess. Yeah, so I need to multiply that through, so then I get here 3 over 2h, 4, and 1. So I've just multiplied over the 2/3 h, and then I get this formula. This is an approximation of y prime that tk. This is a high order finite difference quotient. So this is just a different finite difference. Uh-oh, I think my battery is gone. I need to charge. No. Somehow my GoodNotes has packed in. How do I get this to restart now? It's something to do with my pencil not working anymore. So I'm gonna avoid writing at the moment. I can still move it with my fingers. So does that answer your question? So if you look at the formula here, the first part of 5.6 is exactly this sum alpha s minus r uk minus r over h. And the second part is the right hand side. It's a linear combination of the f's evaluated at some previous points because the h's cancel. And so this 5.6 is how much the u function does not satisfy the finite difference approximation of the ODE. And that's how a truncation error is defined. Yeah. So one of them is basically saying, if I start at on the trajectory, how much error do I make in one step? And the other one is saying, if I put the true solution into my scheme, how much error do I have in how much misfit do I have? And for some reason, when people studied these, the truncation community defined it with dividing by h, and the other community defined it without dividing by h. It's just a definition question. But the nice thing about the truncation error is that maybe you've observed that already, is that the truncation error has the correct consistency, has the correct no. Let's see if now my pen works again. Oh yeah, the truncation error has the correct order, because the local error goes like one order faster than the actual final convergence, because you always lose one by summing up all the individual time steps. If you start with a method that has a local error of order h to the p plus 1, then you'll have a global error of order h to the p. And the truncation error is designed by dividing by h in such a way that it already has the correct order already. Even in the local setting, you have the correct order. But it's only a definition question. That mathematically speaking, you're just scaling by h. I think I said at the very beginning of this chapter, we're restricting to the case of uniform time stepping. So if you have non-uniform time steps, then I think it gets a little bit more involved, the link between the two. So if not every time step has exactly the same length h, but it's like hk, all these methods work also for the case where you have variable time steps. But then the formulae get a bit more complicated, and the analysis between local and global, local and truncation error will get a little bit more so for example, here you will then have an hk, and so although it will still be the same link. It will still be just divide by hk. Any other questions on this part, or is it clear now? Anybody else got some more questions? So I have recorded the next lecture already and uploaded. It's a bit longer, it's 1 hour 50, because I wanted to finish the whole analysis part, which goes to, so I didn't want to stop before giving you this proof here of 5, 4, 10. So I finished all the way to the end of page 84 already. And then I will do a shorter video covering sections 5.5 and 5.6 on Thursday. Okay. If there's no more questions, I'm going to look on Moodle if there's any questions there. I didn't see any earlier. After looking at the one-step methods, you mean? So basically, I think in one of the first videos I tried to motivate it. I'll repeat. So basically, both, I mean, as with many numerical methods, there is different communities that develop methods, and then you have to decide which ones you find are the more important or the ones you want to follow. So Runge-Kutta methods are very popular, but equally linear multi-step methods, in particular the BDF methods, are very popular. And the reason is the following. So I try to do the same as I did in the video. So we're advancing in time and ODE from some time t0 to t1 to t2, t3, etc. Now, when I'm doing a Runge-Kutta method, a one-step method, then I really always think very, very local, in the sense of I define my y. I have computed y0, y1, and y2, and I'm interested to compute y3. And so my question is now, how do I do that? And the one-step method says I'm gonna base it on my value of y2 and some informations on the right-hand side f. And so in particular, the Runge-Kutta methods, in order to get higher order convergence, then proceed in using intermediate stages. So these are let me just change the color back again. So these are the time steps. We call them time steps. But then I introduce stages. So for example, I could introduce 3 stages here, 3 extra stages. So these are called stages, at which I'm evaluating, I'm computing approximations, but I'm only using them in order to compute my final value of y3. So I'm computing I always forget, G is the stage value here. So I'm computing a G1, a G2, and a G3, for example, in order to compute y3. So in order to do so, in order to compute these G1, G2, G3, I actually, in the process of doing so, I evaluate f of some t2 plus CIH, comma, and some value for the second. So I evaluate f at each stage as well. So f evaluated at each stage. So in order to compute y3, I'm, for example, here evaluating f 3 times in the middle. And then I get my value at y3. So this is the one-step method. Now in the multi-step method, people who designed them said, hang on, why do I bother computing these G1, G2, G3? So maybe just to see it visually, we're using information about y and about f of t and y only from this interval. Everything we're doing in order to compute y3 is based on the value y2 that we've computed before and values in between T2 and T3. Multi-step methods say, hang on, we've already spent all this effort of computing T0, Y0 at T0, Y1 at T1, Y2 at T2. So if we want to compute now Y3 at T3, why bother doing extra point evaluations? Let's just take, let me try and get another color. Let's just take the values at the previous times as our points from which we extrapolate the solution. So here we're not using G1, G2, G3, we're using Y0, Y1, and Y2 in order to compute Y3. So we're using not just Y2, we're using Y0, Y1, and Y2. So there's no extra, so no additional functional evaluations. Because at those points here, we have already evaluated f before. To compute y1 and to compute y2, we had to evaluate f of y1 and f y2. So since the function evaluations are the expensive bit typically in these ODE solves, you do fewer function evaluations. So basically the main gain is fewer function evaluations. Okay, so that's now I've sold you why we would do multi-step methods. However, now you might ask the question, why did I bother telling you about Runge-Kutta methods? Because these are cheaper. And the answer for that is that we will see in the next video that the stability of multi-step methods is much lower than the stability of Runge-Kutta methods. So it is not possible. So we will see in the end of this chapter. No, this is the wrong chapter. At the end of the previous chapter, we will see that the second Dahlquist barrier there is no astable LMM of order greater than 2. So essentially, you cannot, all the methods I described to you before, the BDF3, the BDF4, etc., they're all not astable. And so if you want to solve stiff ODEs, you really have to be careful with your multi-step methods. So that's kind of the advantage of the Runge-Kutta methods, while the advantage of the multi-step methods is that we essentially can have fewer function evaluations. Does that give you motivation? And from a point of view of what we learned in numeric 0, it's the difference between interpolation and extrapolation. So here we're using this information in order to get the integral from T2 to T3 or the derivatives on T2 to T3, whereas in the Runge-Kutta method up here, we're using values in between T2 and T3. So here we're using interpolation, here we're using extrapolation. And interpolation is more stable than extrapolation. It's the same as Now you've got me started. It's the same as this craze about machine learning at the moment. So people believe that machine learning solves all problems these days, but in essence, you have the problem which they call transfer learning, that essentially extrapolation is an unstable process. And interpolation, I totally agree. Neural networks and machine learning is fantastic for interpolation. So if you want to know something in the domain between values where you have seen the data, then there is some very fast algorithms to interpolate data. But nobody will convince me that neural networks will ever be good for extrapolation. If you haven't seen something, if you haven't seen whether somebody is walking behind the house, the car will never know that the kid is going to walk out onto the street in front of him. It's just not possible. No car will be able to see through the wall. Sorry, I'm a bit. Um, I'm just in the middle of a conference where we had a whole mini symposium on machine learning. So no, they have definitely their place, but it's really a good comparison here. Extrapolation is much harder and much less stable than interpolation. So so yeah, so Jakob Zech is gonna give a course next semester. I don't know if it's gonna be only for master students or at what level he's gonna do it. There's essentially so there's also some courses by Uli Köthe, which are mostly for informatics students, but I think he does quite a lot of the mathematics as well. But if you really want to know about these approximation properties of neural networks, then that the course by Jakob Zech might be useful. Books, there is such an abundance of books these days. I'm not maybe the best to ask for the best methodology, but for the best book, sorry. Um, but yeah, so I would have to refer you to those people who are teaching these subjects. I am in the process. Next semester, I will work on it a bit because I'm going to do a more philosophical project on neural networks, on artificial intelligence between Wunderglaube und Wissenschaft. And so I will have to read up a bit more if I want to make some informed statements about it. Hmm. Yeah, the difficulty with new subject areas. So the old, I mean, there's some old textbooks on the universal approximation properties on types of neural networks. So, but the problem with new subject areas is that because there's really literally millions of people working on it at the moment, that you kind of have to look at which books are the most popular and the most well advised ones to know which ones are the best. I can point you to, from a numerical analysis point of view. Actually, now I've remembered one thing that is quite good introduction is an article in the Siam Review. Let me just try and find that. I have printed it off and I've been wanting to read it. So that's really a numerical analyst's view on neural networks. Siam Review. I think it was Des Haim who wrote it. Yeah. So this is an introduction for applied mathematicians. It's called, and he will have all the literature as well, so you can then refer to. So this is again, like I said, everybody has their spin on the topic. This is the spin of a numerical analyst. So he's like trained in a similar way to how I am. I'll put it in the post. Yeah. hmm So these are generally quite good articles. I like the so SIAM review is SIAM SIAM is the Society of Industrial and Applied Mathematics, which is the biggest society in applied mathematics. It's so I've been a member for a long time, and it has some of the best journals and books, and they have their sort of flagship publication is called SIAM Review, and SIAM Review has some very accessible articles because they're meant to be for readable for the whole SIAM community, and so they are kind of definitely for final year bachelor students, they should be readable articles. And especially these overview articles like the one I've just sent you one of, they're basically written much more lower level than and since we added another, I don't think they're doing anything on machine learning yet, but another good list of references which I keep on giving. So when somebody asks me they want to do a bachelor thesis in my group, I tend to give them this reference. So this is now really strictly, this is a numerical analysis uh, book series. They're called Acta Numerica from the Latin, and that series of books has per I think per volume per year they have 6 articles or something, or maybe 8. It seems here, and oh no, not all of them. Some of them are back matter. I think it's 6 usually articles on modern numerical analysis topics, and they go back to 2001 or something, or even 1990 something, and you can see sort of the main topics of numerical analysis there. Okay, is that it for everybody? Good. Then I wish you a good week, and I will record the second video on Thursday and upload it then. Okay. Bye, thanks.